Lab 3, Black Hole Orbit. Morgan Jackson, Section MO2, Dr. Greco. In this lab, we are given a hypothetical situation in which a star, in which position data points we know, is orbiting a black hole with a known location and unknown mass. Our objectives are to make a model in VPython based on the data of the star, to explain meaning behind code and analyze model accuracy, to determine the mass of the black hole using Newton's law of universal gravitation, and answer what if and what does it mean questions. Let's start with the values we were given in this lab. We were given the star data file of positions of the star, the mass of the star, delta T, and the position of the black hole. All this is shown here. From here, we can address our first objective, to make a model in VPython by starting to create the necessary code, and from there we can analyze meaning. First, we have to input the mass of the star and the time step, delta T, which is just number of seconds in one day. This is shown here. Next, we have to use a while loop to calculate the velocity at each point as the star travels around the black hole. Since we set the index equal to 0 earlier in the code, we can iterate through this block of code for each position. Delta x and delta y calculate change in positions, and velocity is then calculated in the next line of code by dividing the change in position by the change in time. A loop is the perfect way to calculate all the different velocities over the time step because it includes each one individually. Our next while loop is used to calculate the majority of the rest of the values needed to determine the mass of the black hole. Again, a while loop is necessary because we have a number of different velocities calculated using the prior while loop. Using the velocities calculated, we can use the mass of the star to calculate momentum and then get the changes in velocity and momentum, delta t and delta v and delta t. As you can see here, our next step is to use the variable dp dt to stand for the change in momentum over the change in time. This is just calculated using the variables we assigned earlier, delta p divided by delta t. In this case, Fnet just equals dp dt because we assume the only force affecting the star is the one produced by the black hole. Now that we have written the code to determine what dp dt is equivalent to, we can find the perpendicular components of dp dt and Fnet. The first block of code is focused on dp dt parallel. To calculate this vector, we need the unit vector p hat as well as the magnitude of dp dt. This code is shown here. The next part is focused on calculating dp dt perpendicular. By subtracting what we just calculated to be dp dt parallel from dp dt in the previous slide, we can get the perpendicular component. This method is necessary because the radius of the kissing circle of the star's path isn't known. Finally, outside the while loop, I added these additional lines of code. Remember, the third objective of this lab was to determine the mass of the black hole. We used Newton's law of universal gravitation shown in the lower right. F equals g times the mass 1 times mass 2 divided by the distance squared, or magnitude of r squared. So, inside the largest final while loop, I placed an additional few lines of code. G just stands for the gravitational constant, which is 6.67 e negative 11. The next line shows the position of the black hole that was given to me in vector form. Next, we need to find the magnitude of the difference between the black hole position and the star position. In the equation, this is represented as d squared, or the magnitude of r squared, but I chose the variable r here. Next, we combine these values by manipulating the equation shown in the lower right to get the mass of the black hole. Finally, a print statement is added on the end so that running the program would result in showing the user the value necessary, which is printed at the bottom in blue. That value is represented in kilograms. Once all the code is typed out accurately, this is the model that results. Due to the scale of the arrows and black hole, the model isn't perfect. However, the data that results is accurate in regards to the mass of the black hole. How is Fnet different from the change in momentum over the change in time, dp over dt? In this lab, we assume that Fnet is equal to the change in momentum over the change in time because we assume that the black hole is the only object that exerts a force on the star. However, in reality, that's not the case. Often there are many forces acting on a system. Examples would be those of friction or weight. Those forces all add up to be the net force. Here, since we are only considering one force, the attractiveness of the star to the black hole, we can assume these values to be equivalent. Our next question to address would be, what if a black hole of a different mass was placed at the same location? Would you be able to tell a difference? Yes, we would. In this lab, we assume that only the force affecting the star is the one from the black hole. If the mass of this black hole increased, the force would be slightly more attractive from the star's perspective. The positions of the star would look different, which would result in calculations that are different and ultimately us determining a different mass of the star. This method of calculating mass should always work under these conditions specified. In conclusion, it is now determined that we can extract data about a system based solely on observations made of the system. This seems backwards from prior labs, but the physics concepts work both ways. Newton's law of universal gravitation proves to be extremely helpful in determining masses of unknown extraterrestrial objects, assuming that only one force is acting on the stars in relation to the black holes. This method is extremely important in not only doing physics problems, but discovering unknown facts about the universe in which we live. Thanks for watching.